every for every.
Oh, no, I just want to remember. Okay, we set that for plus z is PRW of V plus PRW of Z, which is PRW of V plus 0, which is PRW of V. But before that we had this that Z is orthogonal to W, right? We had this. And so we said that we want to write it in a verbal format. So can you read what you have written?
Yeah, so I was like, the projection of the vector V on RW,
But the projection of vector of V plus Z.
V plus Z on RW is equal to the projection of V on W, on RW, and Z on RW.
No, but you have to write in this form. Because P projection is a linear,
Yeah.
this is a very, very key word, linear transformation, then P can be written as this first line is simply because it's a linear transformation, and you know we are so many times we do not emphasize on that one, and by default we use it, but this is a very key word because Z is orthogonal perpendicular to W, then its projection on range of W is 0. We draw this and we said that we remember from physics or calculus that if this is the x-axis, this is the y-axis, and if we have a line and we wanted to project it, we said that there is no projection on the x-axis, everything is projected on the y-axis, right? As a vector, if this is a vector. And if we had a vector like that, we would say that this is that much x and that much y, right? So, like this vector is, for example, vector v here is 0i plus, I don't know, alpha j as a vector. Now, so the projection on R is 0, hence projection is so let's do another example. Now, basically, what we said we could represent, we said we can decompose a vector into the projection of the vector on the range of another vector space plus the projection of that vector on the orthogonal complement of that one. Remember here, x and y are orthogonal complement of each other, right? So we can do it for the null space and null space orthogonal complement. Let x belongs to Rn be an arbitrary vector, it's a column vector, we know that. Then any vector x can be written as P of NA x plus P of NA orthogonal complement of x. Which is I minus A plus A x plus A plus A x. And we remember, what is A plus A? V1 transpose V1? No, V1 transpose. And what was I minus A plus A? V2 transpose X. Laura, do you remember what are V1, V2? You said that if A is decomposed into the U sigma V, we can write it as U1 as V1 transpose, because this is basically U1, U2. This is S0, 0, 0.
Yeah.
And this one is V1, V2 transpose. So this V1 comes from here. And we remember that if it was range and orthogonal normal of range, then it would be used, right? So how do we use this formula? This example is another example. Question will be like the question in the exam can be like this. Decompose the vector 2, 3, 4 into the sum of vectors, a vector in NA orthogonal complement and a vector in NA, given A is now, in the exam, definitely you have your MATLAB, for instance, you can calculate your A plus, but here I give you that A plus is 1 over 4, 1 over 4, 0, 1 over 4, 1 over 4, 0. So how do we have to do it? What is the formula? Exactly, the formula is what we have in the right side. Now, which of the terms do we have to use, Laura? You know, we have two representation of we have to do this, right? there are two representations. Let's call it representation 1 and representation 2. Which one is easier for us right now to use?
Given that we have plus and a, the first one.
The first one. So what we have to do, we have to simply do the multiplication. We have to simply say that x is a plus a x plus I minus a plus a x. So it will be, this is for PNA, this is for PNA orthogonal complement. And if you do that, you will see that our vector x is results of this. At them, we will see that, okay, this one is 4 over 2, 2, this one is 6 over 2, 3, this one is 4. Again, your computer can multiply. Now, this is very useful because now we have the we can say that x is addition of two other vectors, and these vectors, each of them can be like a vector in a given direction. Remember, we need to have the projection of vector in different, especially orthogonal directions, because, as I said, like gave you example in pattern recognition, it's very useful because maybe this new projection will make us to have better discrimination of our data. You know that the x is a column vector, but because you don't have much of a space, I write it in this form, the row vector, and I put a transpose on top of it, so you understand it's a column vector.
When does it make sense to use the second representation?
When you already somehow have the SVD.
Okay.
Or if not, I mean, you have a computer in front of you to help you with the calculation. One person can calculate the SVD of A, so you have U sigma V. Then you can see that what one is the V1 and then do it. Both of them will give you the same results. But this can be part of a question, and in previous parts maybe you already have calculated this. Because if you have these vectors, then you don't need to calculate the A plus. And this is a unique decomposition, by the way. This is a uniquely results. Let V be a vector over R, then this notation is a real inner product if inner product of x and x is greater or equal than 0 for any vector x belonging to V, and x and x is equal to 0 if and only if x is 0. Second one is x and y, inner product of x and y is equal to inner product of y and x for any x and y belonging to V. And then x and alpha y1 plus alpha y beta y2 is alpha x y1 plus beta x, y2 for any x, y1, y2 belonging to V, and alpha and beta belonging to R. In chapter 1, we actually define the inner product, right? We define the inner product. And you have, remember that we also discussed what will happen if this is over C. What will happen if it is over C? Right? Do you remember, Ike? Here everything is in R. What will happen if they're a complex number?
It'll still be in R.
No. If you are in R, definitely you are in C, but if you're in C, you are not necessarily in R.
No, I mean the result will be in R. Okay.
Example is that x can be a complex number, y can be a real number, the result is a complex number. We remember that it would be like this, isn't it? X, for example, inner product of x and y is the conjugate complex of y and x if you are interchanging it. Because the inner product was the summation of xi, yi, conjugate complement. In case of C. But here, we are talking about R. Here we're talking about R. So anything that you see here in red is when we are in C. So let's V be Rn, then the inner product of x and y is, you tell me what it is, but it is the Euclidean inner product, or you know it's called dot product. Okay? So filling the blank. X and y, what is it?
Project.
No, it's equal to. How can I calculate it? Come on, we have used
sum of element-wise multiplication.
Yeah, but we mathematically we are writing it in.
Sum of
X is a vector, y is a vector. How do I have to write this inner product? How should I write it that it will be the sum of the products?
Sum of xi, yi for every
we want to write it in the vector form.
Okay. So
what you say is absolutely correct, but I want to see what is the vector representation. We have written it at least on the border over
x times y transpose.
X times y transpose. Ike?
It's trying to process what we're trying to do.
This is equal to x is in Rn, y is in Rn. The result, what is the result of inner product? Is it a vector, a matrix, or a number?
Number.
A scalar. So XY transpose. This is n by 1, this is y by n, then the result is n by n. So it will be
X transpose Y.
but I am sure Ike remembers this. XY transpose. It's very famous. Why it's very famous? It's a matrix, but it's a very famous matrix.
Why?
You made a mistake in the exam about that.
Yes.
What was your mistake? Do you remember?
Yeah, I remember the question, but
The question is that this is a very famous, it produced a very famous matrix.
yeah.
And because of that you forgot why it's famous, you made a mistake in the exam. Do you remember what was your mistake? We discussed it, negotiated.
Yeah, the rank and...
Yes, what was the rank?
The rank is 1.
This is a matrix which the rank is 1. Okay, the rank is 1. So what does it mean? If the matrix has a rank 1 and I'm using singular value decomposition, what do I get?
S is scale.
I will get like U sigma V, but this sigma has only one value
Yeah.
and everything else is 0.
Yeah.
And if you remember, we said that we can write this one in this form. So this matrix, we can do the SVD, the singular value decomposition, quickly. And this alpha is this one. Anyway, I'm erasing. This was kind of a revision. We had a question about it in the Python exam. Let's do another example. I mean, I call them example, but each of them has a very important conclusion or reminder. So this one, we knew it from high school, definitely undergraduate, inner product, dot products in physics, right? Now again, let V be Rn, so the vector space is Rn, then where is an arbitrary n by n matrix defines a weighted inner product. So we can have, we can have a normal Euclidean inner product, or we can have a weighted inner product. And how we calculate weighted inner product of x and y with the weight matrix of Q is this: x transpose Q y. Q has this property: Q is equal to Q transpose, which means that Q is
Diagonal.
symmetric. Q is symmetric. And because this is n by 1, this is also n by 1, we understand that Q should be n by n in order to have everything done. But Q is greater than 0. What does it mean? Which type of matrix it is when we write this? It's positive definite matrix. Now, we we write something very more important, and it is if A belongs to R n m by n, then A transpose belongs to R n by m is the unique linear transformation or map such that x a y is A transpose x y for all x belonging to Rm and all y belonging to Rn. Kind of obvious. I mean, the proof is very simple. You just put them there and you can get the result easily. Suppose A belongs to R n by n, and let Q and R be the weighted inner product with Q and R be positive definite, be weighted inner product on Rm and Rn respectively, then so Q is m by m and R is n by n. Then what is this? What is this? This is a transpose. This is a transpose. And what does it do? It changes the rows and columns. Now we want to define something new. Then the weighted transpose a hashtag is defined as x a y over q is a hash x and y over r. Now I open them. So I have x transpose q a y equals x transpose a hash transpose r y. So qa is a hash transpose R. So A hash is R inverse A transpose Q. You know that X belongs to Rn, Y belongs to Rn. We remember the term orthogonal, right? What does orthogonal means? Like we said that X and Y are orthogonal. What does it mean?
Inner product 0.
So yeah, I mean they are perpendicular to each other. Now we have a new way of defining another orthogonality, and it is two vectors of X and Y belonging to Rn are Q orthogonal. What do you think the Q orthogonal should be for the matrix of X and Y? Q orthogonal means or conjugate with respect to Q. X and Y are conjugate with respect to Q. So X and Y in general, X and Y are orthogonal, as Lars said, it means the inner product is 0. So, but if X and Y are Q orthogonal, then
Weighted inner product.
the
is
weighted
0.
inner product with the weight of Q will be 0. If now we have discussed everything over real numbers, although for some simple ones we have also discussed complex numbers, but let's talk a little bit about complex numbers and all of these things, how they will look like when we are handling not R but C's. Let V be a vector space over C, and then this operator is a complex inner product if we have three conditions. X and X is greater or equal than 0 for all X belonging to vector space V, and X and X is equal to 0 if and only if X is 0. Second one, inner product of X and Y is conjugate transpose of inner product of Y and X. And the third one is X alpha Y1 plus beta Y2 is alpha X Y1 plus beta X Y2, for all x, y1, y2 belonging to vector space V, and alpha and beta big complex numbers. Prove that must be real. How can we prove that? Although x is a complex column vector, but inner product of x by itself will become always a real number. It's very obvious, isn't it? But we try to prove very obvious things. As usual, the proof is already on the board. From the second property, we get inner product of x and x. I switch them, should be the same as inner product, the conjugate of x and x.